So I'm Carla Westphal from Saddleback College, and in this video we're going to be taking an introductory look at L'Hopital's rule. L'Hopital's rule is a rule that allows us to evaluate limits when we get things called indeterminate forms. Okay. So I've written it up on the board here. If we have two functions f and g, and their limits as we approach some number a are both equal to 0. Okay. Then what's happening if I'm looking at the limit of their ratio, f over g, the top is going to 0 and the bottom is going to 0, and that's what we call an indeterminate form. The top being 0 suggests that the fraction should be small. The bottom going to 0 suggests that the fraction should be big, so knowing where the pieces go doesn't tell me where the fraction as a whole goes. And what L'Hopital's rule says is that that limit is actually just the limit as x approaches a of f prime over g prime. It's the limit of their derivatives. Now, of course, that's provided this thing exists. Okay? And in order for this to exist, f and g have to be differentiable. We have to have an f prime and a g prime. Okay? So if this exists, it also holds true if this limit here is infinity or negative infinity. That works. And L'Hopital's rule applies to one-sided limits as well. It also, I've written it out here as if these limits are both 0. It's also true if both limits are infinity or negative infinity. Okay. So in this example, we're going to take a look at an indeterminate form where we get a fraction where the top and bottom both go to 0. Our second example, we'll take a look at an indeterminate form where the top and bottom both go to infinity or negative infinity. So I'm just going to make a note here. This also holds for one-sided limits and indeterminate forms of the type plus or minus infinity over plus or minus infinity. Okay. So if the top and the bottom were both going to infinity, or one of them was going to infinity and one to negative infinity, we could apply L'Hopital's rule as well. Okay, so let's just take a look at an example. Let's suppose I wanted to take the limit as x approaches 0 of sine x over e to the x minus 1. Now, if I try just naively plugging in 0, I would see that on top I get sine of 0, which is 0. And on bottom, e to the 0 is 1 minus 1 is 0. Now, I can't plug in 0, that means, because the bottom is going to 0 and the top is going to 0. Notice my notation. I'm using arrows to indicate that the top and bottom are going to 0. I am not writing that they are equal to 0. I can't write that because the bottom cannot be 0. It can never actually equal 0. It's just getting close. But this gives me an indeterminate form. We say it's an indeterminate form of the type 0 over 0, and L'Hopital's rule applies. So usually when I'm using L'Hopital's, I'll indicate that with a little LH here to say I'm applying L'Hopital's rule, and I'll say this is the same as the limit as x approaches 0. If I take the derivative of sine x, I get cosine of x. If I take the derivative of e to the x minus 1, I just get e to the x. But now, in evaluating this limit, I can actually just plug in 0. That's cosine of 0 over e to the 0, 1 over 1, which is 1. So a limit that would have been very difficult to evaluate otherwise becomes relatively simple as we use L'Hopital's rule. Now, I've given you an example of why it works. That doesn't really address, of how it works. That really doesn't address why it works. I'm going to informally sort of suggest to you why it works. This isn't going to be a full-on proof, but just sort of a suggestion of what's going on. If I take a look at that top function, which is sine of x, that's a continuous function. So the reason that its limit as we approach 0 is 0 is because that's the function value at 0. That function passes through the origin. If I were to draw in the tangent line at that point, okay, the tangent line at this point is just y equals x. The derivative of sine is cosine. Cosine at 0 is 1, so it's going to be a line of slope 1, and it passes through the origin. And we know that near that point of tangency, sine of x behaves kind of like its tangent line. So it behaves kind of like the function just y equals x. Now, if I do the same thing for e to the x minus 1, well, that's also a function that passes through the origin. That's just my exponential growth function translated down 1. And I could draw in the tangent line there as well. Now, this tangent line happens to be exactly the same. It's just y equals x. Because the derivative of e to the x minus 1 was just e to the x. Evaluated at 0, that's 1. So again, it's a line of slope 1 through the origin. But what this means is that near 0, near this point of tangency, sine x over e to the x minus 1 behaves kind of like the line that approximates sine x, which is just x, divided by the line that approximates e to the x minus 1, which is just x. And of course, x over x is 1. And as long as I'm looking at functions that are equal to 0 at some point, the tangent line at those points is going to end up just, or the ratio of the tangent lines is going to just be the ratio of the two derivatives. Notice this is 1 copy of x over 1 copy of x. The x's cancel out, and I'm left with just the ratio of those derivatives. All right, so let's take a look at an example of the second type of indeterminate form we get, where we get the top and bottom both going to infinity. So let's say I've got the limit as x goes to infinity of e to the x over x squared minus 2x. So as x is going off to infinity, e to the x is going off to infinity. X squared minus 2x is a polynomial, so it's dominated by its lead term, and x squared is also going off to infinity. So here we have an indeterminate form of the type infinity over infinity. Again, I didn't write that we literally have infinity divided by infinity, because that would be nonsense. I just used arrows to indicate the behavior of each function. But now I can use L'Hopital's rule. So I can say this is the limit as x goes to infinity of the derivative of e to the x is e to the x over the derivative of x squared minus 2x is going to be 2x minus 2. Now at this point, this is kind of interesting, because e to the x is still going to infinity. And 2x minus 2 is dominated by its lead term, 2x, which is still going to infinity. So we applied L'Hopital's rule once, but we still have an indeterminate form. That's okay. If this is where I was starting, I'd say, oh, I have an indeterminate form, I should just use L'Hopital's rule. So what I'm going to do is just use L'Hopital's rule again. So we get the limit as x goes to infinity, derivative of e to the x is e to the x, over the derivative of 2x minus 2 is just 2. At this point, the denominator is now finite. So e to the x is going off to infinity. Dividing it by 2 is not going to change the fact that it's big and positive, and so this limit is infinity. So you may need to use L'Hopital's rule more than once in evaluating a limit, and that's perfectly legal. So L'Hopital's rule applies for indeterminate quotients, 0 over 0, plus or minus infinity over plus or minus infinity. And that's it for this video.